Okay, hi, it's me again, and in this lesson number 3 of the gas laws and kinetic model, we're going to look at Gay-Lussac's law. And so this will be looking at how the pressure of a gas is affected when you change the temperature of it. So let's go look at the learning intention. And it is 16.10, so 1610. I can describe an experiment to verify Gay-Lussac's law, pressure and temperature, and the formula that we're going to be interested in here is this one here. So rather like Boyle's law, I'll take you through the experiment. It's something, again, like Boyle's law, that you should be able to describe the experiment, which is obviously tricky, having not actually done the experiment yourself. So as before, we have a container. The container has a gas inside. We have the pressure gauge that's connected into the container. Now this is a fixed volume, and all we can have is, all we're going to do is change the temperature. It doesn't show particularly well actually how you would do this, and I have another picture. It's actually in the course notes, which I'm just going to skip over to now. And this, I think, here shows much better the experimental setup. So what we'll have is before in the virtual experiment, and I will go back to that, but you have the pressure sensor here, and that is connected into the flask, which is, or the container, which contains the gas. The thermometer is inside the flask, and you put it in a water bath. Now, the reason I'm showing you this and not just sticking with the virtual physics description of it is that there's a couple of important things here. Number one being that the entirety of the flask is submerged in the water. So that's number one, all of the flask is submerged in the water. And number two, the thermometer is placed inside the flask and not just in the water. And so you're actually measuring here the temperature of the gas rather than the temperature of the water. There will be an occasion where you'll be asked to comment what's wrong with this experiment, and the two most common ones are for this, that you'll have the thermometer placed outside the flask, which we would say was wrong, and then the water level will be somewhere around about down here. And so not all of the flask is completely submerged. So back to the virtual physics, and what we can do is to explain in terms of kinetic theory, which is our other side of this. We're going to qualitatively explain in terms of kinetic theory about what's going on here, and then we'll look at a quantitative approach by taking some results and doing some graphs. And so qualitatively, what's going on is that as you increase the temperature, and I can increase the temperature just by sliding this up, and I'll do it really quickly just to show, and hopefully you'll be able to pick this up in the video, that as it's down at minus 10 degrees Celsius at the moment, but as I slide it all the way up, then you should be able to detect that the particles are now moving much quicker. Let's go back. And so there, I'm hoping that comes across. That's what's happening. But essentially, what we're looking at is as you increase the temperature of the gas, then the kinetic energy of each particle will increase. Now, if it's moving faster, it has a greater kinetic energy. If it's moving faster, then it's going to hit the container walls harder and more often. And this is going to lead to an increased force per unit area upon the container walls. And force per unit area, remember, is pressure. And so the steps involved in describing, using kinetic theory, what's happening to this is, first of all, as the temperature increases, the kinetic energy of the particles increase. Therefore, they hit the container walls harder and more often. This will lead to an increase in force and hence an increase in pressure on the container walls. So I've given the the qualitative explanation away, which I guess is kind of common sense, that if you increase the temperature, you'll increase the pressure. But let's go and look at some real data from an experiment, and then we'll get some graphs done. Okay, so we've done the experiment, we've recorded some data. If I can, let's just zoom in here a wee bit. So we have our different temperatures, we have our pressures. And the first thing that we're going to do is, well, I guess we can plot a graph of temperature against pressure, and let's just have a look at what this looks like. And so again, I'm going to do this really quickly. As before with Boyle's law, if you need a little bit of extra help with how to produce the graphs, then there's a separate video on that will be uploaded concurrently with this. So check that out. But for now, I won't explain how I'm doing the graph because there's a separate video for that. But I will explain what the graphs mean. Okay. So we're going to add our trend line in here. We don't need this. We'll put in some minor grid lines, horizontal and vertical, and we'll get our axis going to 0. Okay, so this pretty much looks like it's good to go. Okay, remember what we're trying to do. We're trying to find some mathematical relationship between pressure and temperature. And looking at this, well, we have a nice straight line of a trend line. And so there is a relationship here. It's a proportional relationship. We can see that as temperature increases, pressure also increases. But for us, it's not much use because what we're doing, we're really wanting something that is going to go through the origin, and this is substantially higher on the y-axis than 0. So it obviously is not a direct proportional relationship. And if we were to try and figure out what we're actually wanting to do is we're wanting to extend this back. We want to extend it back until we find out an intersect. And so if I open up the axis tool again, and I'm going to do this now, minimum value is 0, so I could try minimum value is minus 100. It's still not there. 200. So what you can see is as we extend the axis, the x-axis back, the trend line is continuing and it is coming straight down, but we need to go a little bit more. We need to get some more, so go to minus 300. Some of you may have already figured out where this is going, that and as we'll see here, now it's no good really to analyze what's going on here, so I'm gonna just change my scales a little bit. That's fine. I can do this. Okay. Might get a bit busy if I do this. We'll see how that looks if I zoom all the way in. Yeah, we're not going to get that at all. Okay, hopefully this will allow us to see something. Okay, and so if we look at this part here, Again, this is taking a bit of adjusting just to get right, but what we can see is, so if each major division is 20 degrees Celsius, then each smaller one would be 2 degrees Celsius. So we've got 1, 2, 3, 4, 5 there, and so that is minus 270, and then minus 272, and it falls right in the middle, so minus 273. Where have I heard that number before? Minus 273 degrees C. It is, of course, absolute zero and 0 Kelvin on our new scale that we made up a few days ago, and the Kelvin scale, where 0 Kelvin is minus 273 degrees C, and this is why. So if we look at the graph a little bit more holistically, then what we can see is that pressure is directly proportional to temperature if we use a Kelvin scale. So if we say Kelvin is 0 Kelvin at minus 273 degrees Celsius, if we just say that that is 0, then we can redraw our graph, and I'll go through this in a second, and then we have a directly proportional relationship. If we use it as 0 to 0 for Celsius, then the relationship, remember at the start, is not directly proportional. But if I were to take, so let's go do that anyway, let's go insert a column, and then we'll do a copy here, but instead of this we're gonna have Kelvin. We're going to say that that is that, and remember for Kelvin we want to add on 273 degrees, so at 78.8 degrees Celsius will be 351.8 Kelvin. Now what we're going to do, I'm going to shrink this graph way down here, and I'm going to plot a new graph, but this time temperature in Kelvin against pressure. Okay, now you're looking, well, wait a minute, what does that look like? It doesn't look anything like you're saying, but remember we've got to change the scaling of it. Set our minimum value, oh dear, minimum value to 0 now. We're going to add in a trend line. We're going to get some grid lines done. Look at that. So here we've got something which we can work with. So for temperatures that are in Kelvin only, we can say that the temperature in Kelvin is directly proportional to the pressure, which means if we increase temperature, pressure increases, but furthermore, if we double the temperature, then we are going to double the pressure, and so on. So as we did before, I'm going to go back to the course notes, and here we are. And so this is on page 16. We have our dummy results here as well. We get a new graph drawn, and our conclusion for this is that pressure is directly proportional to temperature, but only when it's in Kelvin. So this is why we say TK. So pressure is directly proportional to the temperature in Kelvin, which again, as same as Boyle's law, we have pressure is equal to a constant times temperature. Rearranging for this, well, we take T in Kelvin and bring it down here to leave that as a constant, so pressure over temperature, and that is our relationship for pressure and temperature, which is known as Gay-Lussac's law. Pressure over temperature is equal to a constant. Okay, so we'll look at some worked examples and then we can go on from there. So, as before, we can have two containers. You'll always see in these questions that it'll tell you that it's a fixed mass of gas, and that's a standard thing, that all of the gas laws equations will only work where there is a fixed mass of gas. And in the example of Gay-Lussac's law, we're going to have a constant volume. So I'll just put that in there at fixed mass and constant volume. So we're going to have container 1 having pressure of just 1 atmosphere again, so 1 times 10 to the 5 pascals, and let's just room temperature, so we can have 20 degrees C. Now what would be the pressure if we were to heat this to, let's say, 100 degrees C? Then we're going to look for pressure. So as before, we have a relationship which is pressure over temperature is equal to a constant. And in practice what we would do is we would write P1 over T1 is equal to P2 over T2. Okay. This would be P1, this would be T1, T2, P2. And I'll get a little table. So P1, T1, P2, T2. One of the most common mistakes and one of the easiest things to do is to write down here 1 times 10 to the 5 pascals, 20 degrees C, and you're going to think, great, it's 20 degrees C, you stick 20 degrees in the formula, and you forget altogether that actually the formula only works if your temperature is in Kelvin. And so we need to convert this into Kelvin, and of course to convert to Kelvin we add 273 degrees onto 20. Now I'm sure I probably could add 273 plus 20 myself, but I have seen it being done before. I've done it before myself. You add it wrong and it's a daft silly mistake, so just be doubly sure. Use a calculator. 293 Kelvin. We're going to look for pressure 2, so I'm going to put a question mark there. T2 was 100 degrees C, and that is going to be 273 plus 100. We can just about do that. 373 Kelvin. Then we can do one of two things. So we can make the substitution first. We can put all the numbers in and rearrange, or we could rearrange first just for P2, which is what I'm going to do. And so we've got P2. Now, 4 variable formula. It's not like your standard 3 variable formula: speed, distance, time, Ohm's law, numerous other formulas. And so a triangle is no use here. You can't have a triangle for this because there's 4 variables, and it just doesn't really work. So what we would have is we just need to cross multiply. Now, if you remember, the rules for cross multiplication is you can move a variable from one side of the equals to the other side of the equals, but it must move diagonally. And to find the variable that we want, in this case P2, it must be on its own and on the top. So it's already on the top, but it's not on its own. We need to get rid of T2, and we do that by moving T2 diagonally up to here. And so we're going to be left with P2 is equal to P1 times T2 over T1. Now we can make our substitution. And solve in the calculator. So that will give us 1.27 times 10 to the 5 pascals. Okay, right, we'll do a second example. Okay, so we'll have a popular brand of soft drink here. Now this will be a volume of 500 milliliters, which of course the volume is fixed because it's not been opened yet. And we'll have it at a slightly higher pressure. So let's go that it's been shaken. Nope, it's been heated up, and we're going to have our pressure 1 being 1.1 times 10 to the 5 pascals. And it's been heated up so that it is at 60 degrees C. Now, if it returns, what temperature will it be when it returns to atmospheric pressure? So let's set P2 at 1 times 10 to the power of 5. And that's T2, so we'll put a question mark there. Gay-Lussac's law is P1 over T1 equals P2 over T2. We're looking for T2 now. Right, so I really wanted to do this because it will show you the different rearrangement. Again, to reiterate, to cross multiply, what we need to do is we need to get the variable on its own and on the top. It's not on its own and it's not on the top. So what we're going to do, well, first of all, let's make it go on the top. So we drag it up here, we pull it up to here. So we've got T2 going up there. But now it's even worse, it's not on its own at all. So bring P1 down there, and then T2 goes up there. So we're going to have T2 equals, this has come up here. The P1, P2 stays where it is, P1 comes down there. And then our T1, that goes up there, like so. No, that's T1, isn't it? Of course. Okay, super. Now, as well, don't forget that 60 degrees, we're going to add on 273 to get 333 Kelvin. So we have P2, 1 times 10 to the 5 times T1, so times 333, and then divided by P1, which is 1.1 times 10 to the power of 5. and that's going to give us 302.7. So let's call it 303 Kelvin. Don't forget, this is not like specific heat capacity. We're not talking about a change of temperature. This is the actual temperature, 303 Kelvin. We do not need to, unless it asks us, we do not need to convert back into Celsius. It's fine like that. That's our answer there. If we did want to convert to Celsius, well, we just take 273 off it, and we would be left with 29.7, so 30 degrees temperature change. 30 degrees Celsius. But we're really not going to do that unless this question specifically asks us to do it. Okay, and that is Gay-Lussac's law. Thanks for watching. As ever, any questions, just give me a shout. Okay, thanks then. Bye-bye.